In this image you can see a standard gear. Because it's not easy to understand the shape of a gear, firstly some theory. The gear rolls over its pitch circle. The calculations of ratios and forces are all based on this circle. So, it's very important, however you can't measure it on an existing gear. On the pitch circle you can find the circular pitch, which is equivalent to the arc length of a teeth plus a hold. If you know the circular pitch, you can calculate the pitch diameter. With that diameter you can calculate a gear modulus. This is a commonly used method to determine the main dimensions of the gear. When you have multiple gears, the modulus have to be the same to let them interact smoothly. The center distance is important when you have multiple gears. You can calculate it easily. With the gear modulus you can calculate the inner and outer diameter, wherewith you can calculate the clearance. When two gears act on each other, the touching surface is at an angle, namely the pressure angle, and it is standard 20 degrees for modern gears. The pressure angle can be measured over the line perpendicular to the center line. Tangent to the line of action are the base circles. Enough theory. Let's start with creating the variables. It's better to take short variable names to save you the hassle of typing long names while modeling. These variables can be changed in a later stadium. With these variables you can also make some configurations of the gears. I like to work with variables when I need to do a lot of calculations with the same dimension. We're starting with drawing a base cylinder with the outer diameter. When you use variables, don't forget to place them in quotation marks. Then the cut extrude. This starts with the most important shape, the involute. Engineers struggled for a long time to find out that this is the optimal shape for straight gears. The shape is determined by the parametric function of an involute. The first part is the radius of the base circle, which is the starting point of the involute. The maximum is around 0.7, but to be sure, set it to 1. The part of the sketch downside the involute doesn't make any sense. So, make it just straight. Draw the inner circle and the pitch circle. Make the pitch circle as construction line. Make a contour and close the sketch and give it a cut extrude. Then, rotate the gear so that the flat face is horizontal. This makes it easier while assembling. Then, mirror the cutout. Note that you need to turn on the geometric pattern. Give the sharp edges a fillet to prevent stress concentration on the teeth root. At At least, pattern the faces around with the number of teeth. The gear rack is comparable with a normal gear, but instead of an involute, you use a straight line. Start with creating the variables and draw one teeth. Draw a center line and a pitch line. On the pitch line you can set the teeth width. This is equal to the half of the circular pitch minus the backlash. Extrude the body with the thickness and give it a linear pattern. The distance is exactly the circular pitch. The last part is the base. You can do it manually, but sometimes it's useful to automate it with a mathematical equation. And that's it. Let's go on with a simple assembly. Start with a holder. The center distance for the two gears is equal to the sum of the pitch diameters divided by 2. The gear rack position is measured on the pitch line. This needs to be tangent to the pitch circle of the gear. Place them into the right position, but keep it movable. Apply the gear mate to the circular surfaces. Apply the gear ratio. This one works. Now the gear rack. To do this, you need to make the sketches with the circular pitch and the pitch line visible. Select the rack mate and select firstly the pitch line, and then the pitch circle. Well done. It works fine.